Maybe this is a good moment to ask you who is here for the first time. If you could raise your hand. Okay, it's good to see new people. Who's here at least for the second or third time? Okay, we've got a couple of you. Who is here, let's say, for the fifth or sixth time even? Wow, okay. Thank you so much. So statistics were taken. Some people were taking notes. Don't blame me. No, but I'm joking. I just want to see whether this code dive, is still valid. It's still strong. I was told that we are really one of the best in the world. So instead of just trying to boast about and whatever, I just want to say hello once again to all of the audience inside this room, to all of the audience on the other side of the internet. Whatever you're doing, just leave it, please, and concentrate now once again. We'll be, setting you into the proper mood, into the code diving mood once again. But applause, actually, for the very beginning is something that gives power not only me, but also the speaker. So please do it for us right now. Thank you. Okie dokie. This will be something that I really would like to send you straight away from this place to another. It's not very far from here. If you're from outside of Wrocław and Poland, I will tell you that we have a special home to only Neon Museum in Poland. So the Neon Side Gallery, this is how it's called, is an open-air courtyard. It's filled with glowing vintage neon signs from so-called PRL, so the communist times, just here from Poland, from Wrocław, but not only. It's a nostalgic and very trippy place, so you can just walk through post-war design and just have a look. And it's just around the corner, so please do not waste the chance. Normally, like people say, hey, Maciej, what's interesting in Wrocław? And I say, it's definitely one of the sightseeing spots that you should be visiting. So please feel more than welcome to go over there. Let me remind you, only Neon Museum in Poland, just around the corner right here. You can just have a look around. Okay. That's it. No more Wrocław. Just concentrating now on people. We have another person with us. Let me introduce him to you properly. He's a senior lecturer at Yale, such a minor little university somewhere around the corner, where he teaches systems, graphics, and software engineering. And please pardon my joke. So his research dives into performance, visualization, and graphics. Outside academia, he consults as a 3D graphic engineer in C++, and he shares his love for code on YouTube. So maybe even my son probably might have watched you. Anyways, so Mike's all about making complex tech click and having fun doing it. And he enjoys creating programming content at is a very simple address. It's just youtube.com/c/Mike Shah. So, and now please listen carefully. He has also run 3 marathons. Let's watch a quick video that would show us Mike celebrating sports achievements. So I hope the video will somehow be set on. Shall I go further, or is it enough? Yes. It's enough. Okay, let's have a look. Unbelievable. Yeah, I'm not surprised you're doing that, okay? So 3 marathons altogether, but today he will be marathoning in a completely different manner. So essential tooling for safer C++. Please, just do your best to make this room as noisy as possible for Mike Shah.
Thank you. All right, thank you very much. Thank you very much, everybody. Thank you very much for the warm greeting. This is my first time in Poland, and it's been an absolutely wonderful conference with many wonderful talks here. And thank you also for just showing me running at mile 10 instead of mile 26, where I'm actually moving faster in that video. So as mentioned, today we're going to be talking about some essential tooling for safer C++. And we've had a lot of great talks, again, as mentioned, about things like contracts that we've dove into. So in a way, I'm going to take you back to just talking about, how did we get there to the safer stuff and talking about some of the features that are available in the language, the standard library, and tooling in C++. So without further ado, we'll get into it with the abstract, again, that hopefully you've read previously. Again, a little bit about myself, as mentioned. Primarily, I do teaching. So again, thank you for that introduction. And again, you can find me on YouTube talking about all sorts of computer science stuff that we care about. Primarily, of course, C++. OK, so enough with that. Getting into the talk here. So a question that a lot of folks ask me, especially in school, students, professionals, even when I do consulting, is why am I still using C++ in 2025? And beyond. There's a lot of programming languages out there. And in particular, there's a lot of systems programming languages out there as well to choose from. And this is a great thing for us as a community, as software engineers. But when I thought about this, there's really two major reasons that I love using the C++ programming language. Number one is the flexibility of the language. So again, C++ being a multi-paradigm language, I was just at a session talking about using C++ as a functional language. And of course, we can write generic code, procedural code, object-oriented, and so on and so forth. Makes it very expressive for the types of problems that we need to tackle. Of course, there's a variety of C++ compilers. We're going to be talking about GCC, Clang, MSVC a little bit throughout this talk. But basically, it's supported everywhere and on major compilers for any system that you have, any operating system, embedded devices, and so on. And C++ really is a language that can scale with you as you grow. So as a programmer, as you improve your skills over time, there's always another level which you can achieve with C++. So ultimately, the flexibility of the language is a wonderful thing. And reason number two, whenever I think about C++, or if I have a choice to choose between tools, it's really performance. That's one of the major reasons, and I think a major reason why many of us are drawn to it. So various industries, finance, gaming, graphics, this was mentioned as my background, the AI world, automotive, et cetera, these are all industries that demand high performance, and C++ offers that. So in my mind, looking forward, at least for the next 5-10 years, I don't have a crystal ball to look further than that. I can say that any domain where performance is demanded, I think C++ will still be there, whether maintained or perhaps extended upon. So again, that's just my prediction. There will still be C++ code in these high demand and high performance industries. So talking a little bit about this reason number two regarding performance, again, C++ historically has been, this has been a foundational tenet of its design, performance. So this thing called the zero overhead principle, which has been mentioned a few times today, is one of the core principles when designing the language, saying, first and foremost, you do not pay what you do not use. And second, what you do use is just as efficient as what you could reasonably write by hand. So this means things that go into the standard library, the language, the type of stuff where if you looked at the code that could be generated from the language, at the assembly would be reasonably close or, again, the same thing. So again, this is where we get some of our performance from by default in the language. But with that, with these two reasons, flexibility, so the power to do anything, and performance, the ability to do lots of things, I wanted to share this ancient proverb with you, that with great power comes great responsibility. So we have to be responsible, right? We've got this really powerful tool. Even coming more, so that was from the movie, but this is from the comic book. Has anybody actually read the comic book from Spider-Man? All right, not as many. OK, I'm the biggest nerd here, I guess. But basically, in the actual comic, there's another line that was omitted from the movie. It says, with great power, there must also come great responsibility. And I think that's very important, that distinguishment, that we need to be responsible, right? We don't just get responsibility by using the language or the power. So we have to sort of choose how we use this language and some of the tools that come with it. And again, we shouldn't forget that C++ has evolved from the C programming language. C is a language that's 50 years old, more than 50 years old at this point. C++ should be about 40 years or turning 40 years old at this point. So again, they've been these performance-first programming languages when, again, performance was very necessary for the early days of computing. So talking about some of the actual design, the different translation units and how they were structured. And this is something that we carry with us today. But performance in the past, well, again, it's still necessary in the present. So again, we need these demands here. But again, safety is very, very, very important today because much of our world is built on top of software. So we need safe languages. So safety first. Can that apply to programming languages? Well, we've seen this. This was mentioned at part of our opening today of this conference here at Code Dive 2025. Various government agencies, businesses, corporations, and so on have released various reports with this, how safe is C++, should we transition, or the recommendation to transition to memory-safe languages. This is a reality, right? So when it comes to C++, we have the tools to write safe code, right? We've done this. The world has built much of its infrastructure on top of C++. But again, it's relying on the programmer to do the right thing with these tools. So again, we're given great responsibility. So one of the goals today is to show you some of these tools for how we can write safer C++. So this will be an overview of essentially some of the essential features of C++, the language, the library, and tools that I think everybody should know or at least have some exposure to. Maybe you're using some of these tools already, that's great, but hopefully this will kick off the discussion at your company or within your group or as a student about how to write better C++ code. Now, again, this theme has come up many times today regarding what is safety. And safety, again, is one of these sort of loaded terms, so it can mean lots of things. So when you talk about safety, maybe it means security safety. Okay, so passwords, authentication, making sure some malicious hacker can't break into your code, these are all important things here. So that's one form of safety. Performance safety, that could be another sort of term, maybe not the first thing we think of when we think of safety, but oftentimes we have requirements on real-time systems, maybe in an aviation system or the braking system of cars, where we want something to work really, really quickly, because again, that's part of the guarantee or necessity of some physical device that we're interacting with software. And of course, there's the software programming language safety, which revolves around memory, and of course, the logical correctness of software itself. So things like avoiding memory leaks and these sort of vulnerabilities that also go into security, avoiding accidental failures, and being able to mitigate or handle failures appropriately if there are errors, and of course, looking at other things in the compilers and so on. And there's yet more different categories of safety depending on where you're going in the stack, on your network, or the actual hardware and failures and so on. But broadly speaking, there's three ways to look at safety. And the type of safety, again, that I'm going to be looking at today, again, is mostly going to revolve around memory safety and the correctness bugs that we would want to fix in our program. But again, there's many dimensions to this, as have been mentioned today. Now, when it comes to performance and safety, what is the trade-off? What is the trade-off that we have to make here? Because clearly, as I mentioned at the start, for a long time, the power or feature of C++ was a performance-first language. So when I think about that, really one of the interesting things that comes along with that is this quote here, that performance is the currency of computing. And this is a quote that I learned from Professor Leiserson, who's over at MIT. And then he also went on to go and say that you can often buy needed properties of software with performance, which I think is a nice way to think about this. Because again, software engineering, computer science is really all about trade-offs. So if performance is our currency, what can we spend to get those safety properties? There's this other quote as well from Alexander Stepanov, who is one of the most influential creators, the primary creator of the standard template library that many of us use in C++. And he also said, another benefit of striving for efficiency is that the process forces you to understand the problem in more depth. And I also think that's very interesting, because if we think about writing efficient code, oftentimes in order to do that, we have to understand the problem that we're trying to solve. If we understand the problem that we're trying to solve, well, then we should have some idea of where are the edge cases. Where could this go wrong from a safety perspective? Where could we spend some time making our systems more robust and able to handle errors, more fault tolerant? So if, again, one other way to approach this too is to say, just understand the problem first. Don't even worry about the programming language, right? Figure out the algorithm, the correctness, the complexity, right? If you want to think about that from a performance standpoint, doesn't again matter what language, but once you figure out the problem and how to solve it, then there's no reason you can't dive into some systems language like C++ and solve it in the most efficient way. All right, and I think this sort of idea of just understanding the problem also feeds into the idea of what does correctness mean. Right? We've looked at or heard about contracts today, so what are those pre and post conditions? If you understand the problem, you should be able to define what correctness means. Okay, so again, the premise of this talk is that I can buy safety in a language like C++, where I have performance. I do have to spend something, though, as a programmer. Maybe that's my own programming time, figuring out the problem, how to solve things. Maybe that's compile time. Maybe that's run time, investing in tools, and so on. And that's what we're going to look at today. So today, I'll show you some tooling for helping achieve safety in the C++ programming language. And we'll go ahead and walk through some of the features here. Okay, so again, our goal is to maximize C++ for some property that we want, whether that's performance or to spend some of that performance for safety, and otherwise just have some exposure to various tools here. In all the programming languages, whether you're looking at the D language, which was mentioned earlier regarding contracts, or Rust with its borrow checker, Ada, which has really leaned heavily into contracts and software correctness, or Haskell, which focuses on being a pure programming language, they all have some trade-offs that they've made for safety that you opt into at some specific level. So again, it is interesting to look at other programming languages, see where they make these trade-offs, and see what you can borrow and implement in C++. It is a general purpose programming language. You can build things. You can build a garbage collector, borrow checker, all these things, right? And we've seen this done by folks in our community, like Sean Baxter with the Circle compiler as an example. Okay, so what kind of safety properties can I buy in the C++ programming language? All right, so I'm going to look at things from at least 3 places where we can buy our safety properties. And again, our currency is performance. I'm going to look at the language level first. So what do we just have as far as keywords, syntax, things that were important enough to bake into the language. The library level, primarily looking at the standard template library. And then we'll go to the tooling level and look at what I think are some essential tools in C++. And again, you can buy safety at different levels of your software or hardware stack. Again, things like networking. If you're a network engineer, might have other levels to this in terms of the hardware or protocols that you follow. But again, three things for today. Okay, and first looking at the C++ language features for safety to achieve our goals. And this isn't an exhaustive list, but I do want to go through a few, again, features that I think are really important as far as the syntax or how we're writing correct code and getting things like compile time safety, and even some of these features, how they inform runtime. So when our actual program is running, the runtime safety. So these are a few of my favorite essential tools that I think everybody should know. This is not an exhaustive list. And neither will all the categories be that I show, but I think it is at least an essential list of a few things that you could look into or should explore if you haven't already. So the essentials. So the first and foremost is const and const correctness. Probably one of the first things that you learn about, or something you'd learn about if you took a C++ course, or when you learn about what the const qualifier is. It basically helps enforce immutability. So again, this is a compiler thing that is enforced in a C++ compiler, as well as many other languages. But basically, compile time says, hey, you can't mutate this value. And as a general rule, if you're not sure, I mean, you should be sure, hopefully you understand the problem that you're trying to solve, but you could default to const, for instance, for your variables. So to avoid mutability, limit your sort of state changes that you have, this is the idea of const. This is also can be a default for member functions. So for example, if I draw your attention to some code here at the type here, for the struct from lines 6 to 13, I have const here, which basically makes this field, the this.m field, const. Okay? It took me probably way too long to put that picture in my head that it was the this pointer that's actually become const when you put that there, but that's the idea, right? And then I avoid some mutations and have some guarantees when I call that member function. We also sometimes use const in terms of the parameters that we're passing in. So we have some guarantees or ideas about the data when it's coming in, what state it'll be left in. So again, you'll see this sort of const, and then when you're passing by reference can be a good thing for performance and, again, correctness. And just as a note, if you're casting away const or you see that, that again might be a code smell. That might be not understanding the problem. Again, there could be reasons to do that, like if you're working with some library or something. But again, it's something to look out for. Generally speaking, trying to work with const and being const correct is a good thing for a code base. Now with const, which has been with us since, well, quite some time, at least C++, for many years, I mean, as long as we've had it in C as well. But in C++ 11, we figured out, hey, this is kind of a good idea. Can we add some more power in thinking about some of these things? So const can help us, again, with the correctness as far as mutating state, but we also got const expr in C++ 11, and then const init and const eval in C++ 20. So first talking about const expr, which is the example I have here, that's some sort of, it's an ask of the compiler to say, hey, please try to evaluate this if you can at compile time. And if you can't, let me know about that. And what's the big thing about being able to compute something at compile time? Well, that's the best time to capture an error, if there is some sort of logical error in our computation, before it gets to the actual user. So that's really a power of const expr. Now, of course, with evaluating things at compile time, what are we trading? Well, we're trading maybe some time at compile time to do something and to make some evaluation from the compile time engine. So that's one of the trade-offs. But what we also get from const expr is, because this has to be known at compile time, this value, this can greatly reduce the undefined behavior that we have in our code. Because again, the compiler has to know what it's computing if I'm doing some sort of computation before it generates the code. So this is part of the guarantees we get with const expr. And throughout this talk, you'll see some of the references that I have that you can look at the slides after the talk, but there is the 2017 talk by Jason Turner and Ben D, const expr all the things. And they have a follow-up, I think it was this year or last year, on const init or const eval all the things as well. So you can read a little bit more about some of these advantages. Now, along with const expr, we figured out, hey, there's some other good ideas here. So const init and const eval were added, which have guarantees about being able to initialize something at compile time or evaluate something. So you can kind of see where the language is going. And if you look at the standard over time, we're getting more const expr functions in the library and so on. OK, so that's const expr, one of the essential tools and the following C++ 20 features. Other safety features, assert. And this is something that's checked at runtime. We've seen a lot about cassert throughout today. But again, basically the idea is that this is a macro that can check some fact about our program, some behavior that if it's not passing, if this isn't true, whatever the statement is that we're asserting, something so wrong has happened that we want to basically abort program execution. So this shouldn't cost the user anything when we're running, because these are for us as developers. We should have lots of assertion statements. Now, what's going to happen with C++ 26 and beyond, right? We'll see some of these assertions sort of become contracts and have more power with where we capture these legal or illegal behaviors. So just a note on assert there, I should all know about. And again, you can see how this is enabled or disabled. I've got the flags below with defining end debug, so if you want to turn off your asserts, or adding in debug. And again, you don't have to read the code there, but just notice that the one on the right, there is more code because that's where the asserts are being compiled in. So you can actually look at the assembly and see the difference here. That's what you're paying when you have the assert at developer time, but hopefully you're again capturing more bugs in your continuous integration systems and so on. Now, with C++ 11, we also got static assert, where you can check bugs at compile time, because again, doing more computation at compile time can be a big win. Again, what are we trading? Well, doing more work at compile time. But we're able to check things like sizes of things, assert facts, assert anything about our const expr functions with static assert. So again, this is another essential tool. One that goes with this, fixed with types in C++. And again, depending on your applications that you're working on. I've worked on various networking things or in computer graphics where I want to know the exact size of an integer on my architecture. And one thing that we can do is static assert to make sure that we have that guarantee. But we can also just use the fixed width types here, things like int32t, to make sure that an integer is in fact in my architecture 4 bytes of information. Okay, so we have a few different tools there. Now you'll notice here towards the bottom, I'm doing something in this code that's kind of ugly here. I'm doing a C-style cast, which brings me to my next feature, which I'll highlight behind me, and that is static cast. So if you must cast in C++11, you get this other tool here, static cast. It's explicit. I can see it right in the code. I can see, again, maybe I'm transforming the data in some interesting way because that's necessary to solve whatever problem I'm trying to solve. But I can actually find it. And then I can make some decision about, is this good code? I mean, this code's OK. I'm just trying to print out an integer value, and I cast to a short, because otherwise the char would print out. So it's like OK, but it definitely sticks out. So you might say, hey, maybe I can do that better. Maybe I can use printf or something there. And sometimes the static cast might be hidden otherwise, behind library functions and these types of things. But again, static cast is going to tell you what you're getting for that type there. So if you must cast, use one of the explicit casts here. OK, so a few other things that you may or may not have been exposed to are attributes. So again, these are hints to the compiler to help define some expected behavior or property of the code. There's a big list of them, and sometimes we do end up with attribute soup, so to speak, if you end up using too many of them. So again, this is something you're going to have to decide in your domain here. But again, basically, these are documentation in the code here. So if I look at an example here, which I've got here, a few attributes. So there's one at line 5 telling me that this is deprecated, some function. So if I'm migrating or trying to improve some functionality, whether related to safety or not, I can get a warning message for that. On things like case statements, I can get fall through if that's the intended behavior. But the point is, it's explicit. I know exactly that I was trying to do that in my code. So if you want to enforce that behavior, you can do so. So attributes can be a handy way as well, something new to maybe look at. A few other features here. The explicit keyword shows up in a few different contexts, but one where I found it helpful is in constructors. I try to make most of my constructors explicit for my types here. And basically what this can do is prevent from having implicit conversions. So if you are doing casts somewhere, whether they're C style and maybe not as good, or maybe if you're not even intending for them, the explicit says, hey, I must explicitly be constructing this object. I'm not assigning it to a value, as is demonstrated here, where I've got this at line 17, this point type here, which has 2 floating point values, where I'm allowed to just do an assignment there. But in the explicit version at line 27, where I've just declared that constructor explicit, that's not allowed, right? Because I'm not telling exactly what to do. I don't want the compiler to choose for me. And this could be a sneaky thing that happens on occasion in code. OK, more features built into a language, things we should know about. Resource allocation is initialization. Again, one of the best C++ features, one of the reasons I love C++ with one of the worst names. But again, it's incredibly useful for handling resources. Things like files, memory allocation, locks, anything where you want something scoped so that you can have some guarantee about the destructor being called and cleaning up resources. This can, again, be very useful, RAII, because you're guaranteed to have the destructor called if there's some exception thrown right when the stack eventually unwinds. You'll get the destructor called. So again, just helpful feature. Now, what am I paying for this when I'm wrapping something with RAII? Again, I am usually creating a type, so there is some wrapper, there is some construction, but again, this usually ends up being a useful thing. But it's not a tool to solve all problems. You do have to think about what problem you're trying to solve. Again, in graphics code, I use this type of stuff, and I have to be a little bit careful when I'm wrapping CPU resources and GPU and making sure they're not sort of mingling together. And I'm always creating and destroying a resource at the right time, or sometimes it's worth it to have explicit control over these things. So sometimes you can use this as a helpful tool, but again, you get to choose. Okay, exceptions. This again is, there's been so many talks on exceptions over the years, how to use them in C++. You can watch hours and hours here. But again, it's a tool that we have here at runtime to try to catch some error that occurred, maybe something that is beyond what the reasonable behavior would be, but you either maybe are able to recover it or you want a safe way to log things. And again, this can be a useful tool for separating out where the error handling code is from the logic. That's the idea, the basic premise of exceptions. So we have this here. Now again, you have to decide if you want to pay for the cost of an exception, if the stack again has to unwind and you have many exceptions being triggered. So some industries stay away from this, but again, it's a tool that we have and you can choose to use. All right, getting towards the end of our language features, variable initialization, also something that is a large topic, but again, simple win here to always initialize your variables. The exception perhaps being if you have a large buffer, there's no need to allocate if you're just going to override that data. But again, you might want to be explicit about that somewhere in your code. But again, initializing our variables to make sure they don't have garbage with the curly braces. Again, one of these things that when I started programming C++, this wasn't a thing, but now it is, as far as C++ 11 and beyond. And there's been some PRs as far as the PR being a proposal, I should say, in the actual language to do things like this by default. And we'll get into some of the tooling in a moment here where we can set this up as the default. You'll have to decide if that cost of making sure that your memory is initialized is something you want to pay. If safety is the most important thing, it's probably a small cost, but you'll have to measure. All right, dynamic cast. I knew I had one more of these in here. It's a little bit of a funny one to say this is a safe thing. It's safer, again, than probably the C-style cast. But again, when you have to use it, you have to use these things. But it can be handy and explicit to show this off in cases where you have inheritance and are trying to see if you can safely cast from something down the hierarchy. So again, just another mention since I had a static cast here. All right, and I think last one that I have here, and this one's a little bit of a funny one here, thread local. And I think about this one a lot because of other languages that I use here. But when we talk about concurrency, again, data races are a huge, can be a huge pain point if you're not able to figure out how to solve the problem, or if you're trying to figure out if you can enable more parallelism, sometimes thread local data can be a way to do that. So by making your data thread local, that means every thread that you spawn can have a copy of the global or the thread local variables, the variables marked thread local. So you're paying a cost of, again, size for that memory, but potentially this could ease your burden or enable more concurrency in your application. So if you're able to make that trade-off, thread local, again, comes to us in C++ 11. OK, so you get the idea. I mean, I could keep going through or running through various language features here, but we want to look at some other stuff. And again, today I was able to capture a few screenshots from Timur and John Lakewis's talk on contracts. So very big feature coming in C++ 27, and you can see how some of these language features feed into it. So there's, of course, topics of type safety, encapsulation, various rules, and other things in the language. But that gives you the idea. OK, so now a few or fewer library features, and then I'll get into some tools here that are also useful or favorites. OK, so I mentioned the zero overhead rule at the very start. This is sort of one of the exceptions to it that falls in the standard template library. But you'll find a few of these things like .at versus the brackets for accessing an element of a data structure like a vector, where the .at function will do bounds checking. So again, this is, as has been mentioned and cited many times, where bounds checks or stack overflows and these types of things are like 70% of the vulnerabilities found or exploited. So we can do some bound checking by just using .at. Now, again, if we don't want to make that trade-off performance, maybe there are some other tools that can help us just use the brackets operator. In fact, there are. So we're going to talk about hardening the libraries as mentioned there. Other favorite features, span and string view. So if you're going to be passing data structures around, things like span, as noted in line 9 here, is basically a wrapper for affecting your data. It's just a pointer and the length so that you're able to access some data within a type, things like vectors or any other random access data structure here in this example. And you don't have to worry about passing arrays or pointers and or arrays that rather decay to pointers and the size and making sure that you have both parameters correct. It's easier to just pass around the span. So again, this is one of my favorite span and string view equivalently for strings to use. Variant, another one of these types. So we got a bunch of these variant, optional, any in C++. 17, which are tagged unions, and these are basically safer ways to access your data if you have some union, to make sure that you actually have a valid type, to make sure that you're, again, being explicit about where you're accessing that type. So anywhere where you're doing some sort of polymorphism on the type, like you would, so a union sort of a tool for that, a variant can be a useful tool. And optional. So we saw some use of optional, or depending on which set of talks you went to today, you saw some use of optional here. But when it comes to error handling and figuring out what type of thing am I returning, right, error codes are a traditional way to do that. In C, that's typically what you do. But what should the error code value be? Should it just be some integer? Well, what if an integer is a valid value? So again, I have this sort of parse integer bad function labeled at line 12 here. And again, if I'm returning an error code that happens to be the integer that I'm trying to parse, again, that's not optimal for us. So instead, we could have optional, which can return the actual were I able to parse this correctly, or I can return basically the null optional back here. Okay, so this could be a handy way to propagate errors. Now, again, maybe it's not as simple as just passing an integer, let's say here, but overall pretty simple, but something we'd want to be consistent on in our code base. And there's some other interesting things you could do at Jonathan Mueller's talk. He talks a little bit more today about the functional style, where you could do things like value or and then, or these types of transformations. And stood expected, which came in C++ 23, offers some more power to optional, which you can start using as well. Okay, some other favorite safety features coming with smart pointers, but unique pointer. Again, this is basically a way to have ownership. Or when I look at this in C++, I sort of think of, this is the sort of ownership model that you can have. I'm pointing to just one thing or have one owner at a time here, which again is very explicit about who's responsible for cleaning up the actual memory. So unique pointers, very handy. But unique pointer with custom deleters, which is in this example, is something else that can be handy for the actual cleanup of your pointer. A shared pointer and weak pointer are also useful and handy if you want more of a reference counted style of memory. You pay for something for that, right? For a shared pointer, you're sometimes going to pay performance. There's locks behind the scenes. But again, you get an automatic reference counted smart pointer. Okay, and something I just recently gave a talk well over an hour on ranges over iterators for safety. So again, ranges can be helpful for avoiding various mistakes that can happen as far as mismatching of the begin and end iterator pairs, for instance. So again, both ranges and iterators are handy tools. Algorithm is handy. The ranges and the algorithms that are associated with those are also handy. But I found ranges often compose and help me solve the actual problem that I need to solve, and usually in a safer way. Now, we might be paying performance. We might actually be paying debuggability, too, in some cases when it comes to ranges, if you do encounter some sort of error. But overall, they usually express the intent of the problem and can help avoid some of the errors with iterators or by handwriting the algorithm, right? By having these building blocks available to us. Okay, so you can see a basic ranges example there. and more and more and more. So again, could spend weeks, probably an hour or a few hours a day talking about all the standard template library features and the new stuff that are coming and the different tools, but they're there. So again, some of the trade-offs and some of the themes you can see emerging. Okay, so now getting into the tooling side of things for writing safer software. Right, we have a range of tools that are available to us. And again, we need to decide at the tooling level, where do we want to pay some cost here? So when can I buy safety properties from my tool? We've looked at the language. We've looked at abstractions that we can add to our actual language to do this. But when it comes to our tools, again, similarly, at compile time or runtime, we might make this trade-off here to test some property of correctness. So again, whether it's at compile time or runtime. Compile time tools we usually call static analysis, and runtime tools we call some sort of dynamic analysis. So static analysis, this is again where we want to gather some facts about our program before we run the program. And the advantage being, well, we can look at all the source code, right? We should have it, or at least all the source code that we own we're able to look at. But we're not necessarily running over real-time data. So we have to be conservative about the sort of errors that we make. I mean, we could make false positives as well in our reporting tools, but typically a static analysis tool tries to be conservative. But again, you can have it propagate to try to understand, could something happen? So what I mean by could something happen, a static analysis tool might look at this program, our whole complicated program here, and say, hey, is it within the possibility that x could be 0? And depending on the static analysis, here we can't prove that, right? We don't know what the user is going to input, but we could say, well, the range of integers is, on this architecture, -2 billion something to 2 billion something. So it is possible, right? 0 is within that range. So it might flag it, might give us some interesting insight here. So could this program do something? Dynamic analysis, on the other hand, is saying what information have I collected that points to evidence of a bug or an error, whether that is an actual program crash, but it's giving us real values. And oftentimes we get this through instrumentation. Even our asserts, which we were talking about, could be seen as a very lightweight form of a dynamic analysis, but it's giving us some facts about an execution of our program. So in this case, what we would do in that same program where I'm just checking, could this program ever have a divide by 0 error, I'm actually at line 6 doing some sort of logging. Again, maybe that's a macro, maybe that's a helper function, maybe that's some instrumentation that's read in by the compiler at line number 6, but I'm actually gathering that information to see, did this actually happen in an execution of my program? And then I can have some sort of statistical analysis about when or how often will this happen. And usually when we do a dynamic analysis, again, we want to collect some information. How much, if it's performance related, how often we call it a function. In a safety case, how often does it crash? How much memory did we allocate? Did we run out of memory? These types of things. So we can collect any number of statistics from our dynamic analysis. So just a slight look at static analysis. Again, from the same terms. Again, static analysis, from a more formal standpoint, is looking at every execution. Dynamic analysis is just looking at each occurrence within a single execution of a program. Okay, and usually we're checking some property like the correctness, performance, style of our program. Could be any number of things. Okay, and of course, a static analysis, depending on the tool, could actually build some model of the program, some higher level property. You could model the program as a graph. That's what I always tell people when they're building these tools. If you can get your program into a graph, then you can, you have your whole assortment of algorithms that you can run on graphs. I mean, that's essentially what a compiler is doing anyways. But you can, actually run some, simulation or do some data flow analysis of what's happening in your program. Okay, so again, static analysis. We're trying to uncover, all the possibilities of what our program could do, and then, our program does some subset of those usually, especially if it's not a deterministic program, something like maybe a game or some, system that's running. Dynamic analysis is a few instances that we're measuring things from whatever our input data was and whatever our resulting execution of that program was. Okay, so hopefully we're clear on that. Which is better? There's no answer to this. A lot of the static analysis and dynamic analysis, people used to battle each other. But the truth is you just use both. So that's the end of the argument for me. And there's of course hybrid analysis where you feed data from one analysis into the other. So use both. Use all the tools. That's going to be another takeaway of this talk here for our tools. Okay, so now let's get into the tools, essential tooling. When it comes to tooling, you'll see a few themes of different things that we can do here. So the first of which that I want to talk about is fortifying, or you'll hear this term, hardening the standard library here. So in this particular example that I have here, I have an array with a buffer that I've allocated for 7 positions, 7 integers. And shortly after, at line number 10, I try to access something that's out of bounds here. Okay, so this is something that, depending on how you built your library, depending on where that memory is allocated, you may or may not catch this actual error here. So I've run this example on several different compilers before, and sometimes I just get garbage from the stack, right? Something that just happens to be there, right? Within the red zone, within the page of memory that stack memory is allocated, this is fine. No crashes, it just goes along, right? And this is where we get some of our exploits from safety and security. But with a hardened library, meaning GCC or Clang or MSVC has been built with a hardened or fortified library, we can at least start to get some sense of errors here, that there was some abort at this point here. And we can go even further here by fortifying our library here and the libc library here with the debug flags here, and basically start getting more messaging here about what happened, the reason it happened, what we were attempting to do here. So even within this simple example. And you can try this out on other functions like in strlen or with vector or other STL data structures. But basically, this will give you the sort of debug version of the library you can think of it at that'll try to capture some of these errors here for us. So these are the types of things, if you're building your system, say in a continuous integration environment, maybe you build with the fortified version so that you can run your tests and so on and see if any of these errors come up, right? Take out the problem. It basically takes out the risk of me not building with these right flags here, or building with the right version of GCC or Clang here, if you can automate some of this stuff here. But this is the idea here. So this is one of the major wins you can do. Now, along with that, with this idea of saying, hey, let's build our compiler or download the compiler from whatever repository you're using that's fortified, you can actually use a sort of different standard library, the Guideline Support Library, GSL, you'll see as the namespace here. And you might have noticed throughout some of these slides that I've had, again, a ton of links at the bottom informing how to use some of these different language and library tools. And again, those come from the core guidelines, things that are from Herb Sutter, Bjarne, other people on the committee, or and other experts in C++ are committing to. And then we have this actual library that has things like a span that'll bounds check for you. So it's not just that pointer and that length, but actually making sure it's pointing to a valid set of memory here. And there's other sort of neat conditional things that you can do and other safety features along with the guideline support library. But this could, again, be a major win for your code base. Again, maybe it's a development version. Maybe you have different checks on functions with some of these GSL standard library here. But again, this is a big winner that I've been using. And then, of course, the simple, obvious stuff. I don't even know if it's worth it's worth mentioning because I don't probably see it enough, and maybe it should be obvious. But just compiling with things like W error, I consider error warnings as errors. Again, everybody's maybe different on that. Happy to fight that battle offline or in Q&A. But our compilers, again, have a view of all of our source code. So compiling with all these error flags, the pedantic, extra, WAL, and so on, are great ways to reduce and catch a lot of the common problems, right? These very common problems that we have in our language, like things like going out of bounds in a stack, they're well known, so they can also be well supported in cases where they can be proved by the compiler. Now, as far as other static analysis tools, two that I'll mention briefly, the first being CPP check is a really, really handy tool. And I actually ran this on all the examples that I have in my GitHub from today to see what kind of errors I was making, even in these toy examples, and you get a lot. I mean, you get some things that are maybe, not false, some things that maybe aren't as useful, or maybe were by design, I should say. But if you run all the checks, you're sure to find something that you might not have caught yourself. And these tools can also give recommendations on here's how you do things the modern C++ way, or using this library feature that you might not have known about. So CPP check is one that's super, super useful. Clang Tidy is the other one. I know MSVC has its own analysis tools as well, but Clang Tidy, is a simple tool that you can install. You can integrate this into your builds, or any time before you're about to check in code, you can use this. And again, here's just an example of me enabling basically all the checks that Clang Tidy can do. Again, depending on your size of your code base and stuff, you might not want to do this, but per individual file, you can run this and at least see what types of silly things that you're doing. I mean, I have even silly things like, hey, I was the guy telling you about the const rule, and I forgot to do it when I was doing this little example with like a fixed integer. So it'll catch those things to reduce your cognitive overhead. Sanitizers are another big one as far as tools to know about. How many folks are using at least one sanitizer in their code base now? Okay, so this is a pretty good group. That's at least half the audience, I think. Great. So the thread sanitizer, address sanitizer, UBSan, or undefined address sanitizer. Again, super, super useful tools. There's also other sanitizers that are out there. They're not all in the compilers like GCC and G++ necessarily, but there was a recent one, robustness sanitizer, which has to do with threading, for instance, which could also be of use if those tools aren't giving you all the errors that you think you have. So there's the default ones that are in the Clang and GCC stack, but there are other ones in the wild. Okay, so here was a little from this previous program that I ran here. I sillily omitted the locks here. For the classic example of run 1,000 threads, add 1 to some shared value. I mean, interestingly, when I ran this program too, I get the correct result. I get 1,000 at the end that I was expecting, but it still detected the illegal behavior here with the data race. Okay, so again, these tools are pretty good and should be used, should be incorporated in your builds. And with that, you have to mention Valgrind. Importantly, not Valgrind, but Valgrind is the pronunciation from their website for memory leaks. So again, and this is a suite of tools. It's not just a dynamic analysis tool for checking for memory leaks. Of course, here's the classic example or usage of Valgrind if you want to take a look here. But if you compile this with debug symbols, it'll do a pretty good job of precisely finding where that memory leak was. You can instrument this Valgrind tool with custom allocators if you're using them. So if you're building your own tool stack or so on, Valgrind is still useful. And there's a bunch of other useful tools with it, like kcrashgrind and some memory visualizers and so on within that Valgrind suite. Okay, and pro tip, again, use debugger symbols. So again, that was the point of mentioning in the Valgrind example, -G with everything, or -G3 or -G GDB to get even more debug information out. And again, super useful. I gave a larger talk earlier this year at C++ on C on understanding large and familiar programs. And using some of these tools like Valgrind and doing some live examples. So again, here's just an example. Let's see if I have the video already queued up here of just using GDB here. But if you're not using GDB, and I talked about all these examples here, you really should be, or whatever LLDB or your favorite in-house debugger. But basically, this is just showing running a game, and then as the game's running, I'm going to attach to the game here using GDB. and then be able to inspect the source code from there. So I'm just getting the process ID, and then I'm launching GDB, attaching to the process here. That's this step here. I guess I had to be a pseudo user at that point. And simple as that. Now I can see and inspect exactly what the program's doing at this point in time. Okay, so you'll see me jump into the code and look at the actual source. And we get the idea. Okay, and that is Transport Tycoon if you care about that. But anyways. All right, go to the next slide here. Oh, all right, so there's my little guide for GDB. You can just take a look at that later if you haven't used here. But what would even be cooler is if I could say, okay, I don't want to just jump into the program randomly. I actually want to be able to, if I jump into the program, be able to encounter a crash and then be able to step backwards. So reverse debuggers. How many folks have used a reverse debugger here? Okay, good. We have a few hands, but not as many. Maybe you'll get encouraged here. So GDB has reverse debugging available, so you can play the reverse card with GDB. I use a tool from Undo, so you can check that out. RR is another tool if you're on Linux that you can use. And again, basically, you can record what happened in your program and then walk backwards to inspect the state of the program. So again, I'll show that just briefly. I've got this queued up here for 30 seconds here. And I'm just going to show you the basic premise of it here, that, again, you can launch the program and basically be able to reverse step here. So I pause my program here. I'm saying reverse continue, recording the history, and this is at the system call level, so I'm actually able to see what goes on. And then I can reverse next, and go backwards. So, I think this is going to be an awesome tool when we get things like contracts and so on to say, hey, this contract or whatever failed. Okay, go back in there, put a breakpoint on that contract, and when it fails, reverse step from there and see why that contract was broken. So handy tool. It's not going to do the work for you. Unfortunately, you still have to look, but it is another handy tool for us. So let me keep walking forward here. Okay, so we get the idea with our debuggers, and there are some more resources. Some other tools that we have regarding safety and testing: code coverage tools like gcov, lcov, and so on. Could do a full talk on testing as well, but focusing on the tools for code coverage and making sure, hey, are the actual, am I actually testing or have some way to repeat to prevent regressions from happening? Do I actually have coverage of that code? So this is just an example, again, showing you the hello world example of code coverage here. And I can run this multiple times if I want to accumulate results, right? If you have a non-deterministic program to actually see what is happening here. But ideally, you're trying to get enough code coverage. Okay, maybe it's not 100%. I mean, you figure out what the right number is. I suppose 100% is ideal, especially if you're a library builder to be testing your code as you update it. But again, this is a handy tool again. Okay, so getting near the end here, I just want to mention when it comes to safety, we're choosing different language features, we're choosing different library features, we have some tools here, and again, we want to know what was the cost. Well, so profiling, throwing that in here is, again, maybe not the key topic of today, but again, we are saying that we're paying performance to use some of these features. So sometimes folks will ask me, hey, did using this feature, using this algorithm, did it slow down your program? And my answer is almost always, I don't know, I have to measure it. And then they come back to me and say, well, did it run faster? And I say, I don't know, I have to measure it at least 10 times. Cut 10 times, or measure 10 times, cut once, I suppose could be the saying for programs, or thousands of times, right? So anyways, you should know how to profile as you're doing these things, because again, if performance is a concern in your application and you're paying for it to do safety and make sure your program is correct or fault tolerant, again, make sure that you're within the bounds of what's acceptable for your particular system. As mentioned, I've thrown a bunch of tools here. So again, this talk could be a collection of tools, things to think about. Adopt something in your build system. Maybe it's even just your CMake file that has the right GSL library built in, the fortified compilers that are being used with the right flags, with debug enabled, and so on. Make this easy for yourself, or as easy as possible, right? So use the tooling on that side of the story as well, so that you can get the properties of your program that you need. Okay, so with that, hopefully you enjoyed this talk. We took a little journey on some of the trade-offs with C++, focusing more on just what features are available, what tools we have that we can use, so that we're not just writing raw code, but we have a full library. We have all these new language features. We have tons and tons of new language features that are coming in C++ 26 and beyond to make it a safer language to write code in. So again, we want to know about those, and we want to know about and be able to measure the trade-offs. We want to be able to build these features, these safety features, into our tools as well. And last but not least, I have to mention the core guidelines as your, another source that you can look at. That's where I built this talk from. That's where I was learning things from as I've been programming in C++. So take advantage of that. Build on each other's shoulders so you can write better code. So there's a bunch of other nice talks here regarding safety and ways to get more out of C++. So I'd recommend those ones if you want to learn more and follow up. And otherwise, thank you very much for your time and your attention today. It's been an absolute pleasure.
So, my friend, you say you're a marathonist, right? I have never, ever in my life seen such a marathon of data inside 1 hour. So please give lots of applause to Mike Shah.
Yep. Thank you. Thank you.
The very last minutes actually to still trigger our lovely person and just ask some questions. So feel free to grab the microphone. Tomek and Rafa are all over the place for you. So whatever you want to ask, if still, because that was plenty, but let's just see how it goes. So anyone just willing to ask any kind of questions, so please let us know. We're just giving 15 seconds now. And actually, we're doing exactly the same request to the people who are online with us today. If you feel like leaving a question now or later, just do it. Oh, here we have someone to ask a question. Thank you so much.
Hello. Thanks for the presentation. And I wanted to ask, could you explain why recently initialization is done by curly brackets and not by the equal sign?
Pardon, I don't think I got that.
Why the initialization of the member variables is done by the curly brackets and not the equal sign?
Okay. So for the initialization with the curly braces, yeah.
Yeah.
Yep.
Why is that recently more popular?
Yeah, so the main reason is that it avoids narrowing conversions with your type. So if I'm doing something like, in the default case, setting a integer to some floating point value, and I do int I equals 3.14 or something like that, the compiler is going to flag that. And it's going to say, hey, this is a narrowing conversion. Whereas normally, if I just assign it, it's just going to truncate, which, again, may indicate a bug. If we have auto on the left-hand side of something, for instance, we wouldn't catch that. So being explicit with our types and then explicit with our curly braces on the right-hand side is an advantage. Now, of course, with the curly braces, if you have other stuff like a vector type or some of these things, we have to start looking a little bit more carefully because then it's doing the list initialization. And most of the time for those conversions, I think I have a list on there. It will still check that. But just one warning on that is sometimes if you see a vector with the parentheses, that's because it is calling like an explicit constructor for some other reason. But usually if you see curly braces, think, OK, avoiding narrowing conversions, modern C++ style.
OK, yep. Thanks.
Yep, thank you.
Still a chance to ask one, so just let us know. Just raise your hand if you're willing. I cannot see all of you, but definitely want to thank for this question, first of all. And if this is it, then we are concluding our last but one session. Please, a short break, a 15-minute break is now upcoming. But I think Mike will appreciate still some warm thank you from you by just giving some applause. Thank you so much.
Thank you.